everyone. Our group is doing crime rate analysis, socioeconomic predictors of community crime. This is our checkpoint 1. I'll start by introducing the dataset. The dataset was provided by this course, and it is based on the research framework of Bothos and Tompolos. It draws on U.S. socioeconomic and crime data to figure out factors influencing community crime rates. The dataset contains 302 observations, which means the size n equals to 302. And there are 8 variables, of which 5 are independent variables. The variable total crimes per population is the dependent variable y. It shows the total number of crimes per 100,000 population. It is a continuous variable. The variables state and stateful are 2 identifier variables. State is an abbreviation of the state in the United States. There are 39 different states in this dataset, and it is a categorical variable. Stateful gives the full name of each state, which corresponds to the abbreviation in the state column. The variable is also categorical. Percent population under poverty, it is an independent variable x. It shows the percentage of the population that are living under the poverty line. The unit is percentage, and the variable is continuous. Percent unemployed is an independent variable x. It shows the percentage of the population that is unemployed. The unit is percentage, and the variable is continuous. Lemma's percent police on patrol is an independent variable x. It shows the percentage of police assigned to patrol duty. The unit is percentage, and the variable is continuous. Long-run poverty rate is an independent variable x. It measures the long-term poverty rate in the area. The unit is percentage. The variable is continuous. Poverty tier, a grouping variable. It categorizes each state's poverty level into 3 tiers: low, medium, or high. The variable is categorical.
Hello, my name is Neil. So, moving into our research questions and model, the main question we're trying to answer is, do current poverty rate, unemployment rate, police patrol percentage, and poverty tier significantly predict total crime rate across the U.S. communities? We also have a secondary question looking at whether the relationship between poverty and crime actually differs depending on what poverty tier a state falls into, so that would be low, mid, or high. To answer these questions, we built a MLR model where total crimes per population is our dependent variable. So the full model is total crimes per population equals beta 0 plus beta 1 times the percent unemployed plus beta 2 times the percent of population under poverty plus beta 3 times the percentage of population on patrol plus beta 4 times poverty tier low plus beta 5 times poverty tier mid plus our error term. So some quick things to note about the model. Beta 0 is just our intercept and represents the baseline crime rate for high poverty tier states, since high is our reference category. And each beta coefficient tells us the effect of that predictor on crime while holding everything else constant. Now, moving on to our predictions, before running the model, we wanted to set expectations for each coefficient based on theory from our reference paper. So, for unemployment, we actually expect an ambiguous sign, and in the short run, higher unemployment might reduce crime because there are fewer people out and about as potential victims. But in the long run, it can increase crime as unemployment leads to poverty. So this one could honestly go either way. For poverty, we expect a positive sign where higher poverty should increase the amount of crime. For police patrol, we expect a negative sign as more officers on patrol could deter criminal activity. And for both poverty tier coefficients, low and mid, we expect negative signs since both could have lower crime compared to higher tier reference groups. And these predictions set up our formal hypotheses, which we'll go through on the next slide.
Hello, my name is Aishani, and I'll be going over our hypotheses. For each individual predictor tested at alpha equals 0.05 two-tailed, Our null hypothesis for beta 1 is beta 1 equals 0 and unemployment rate has no linear effect on crime, versus our alternative hypothesis where beta 1 does not equal 0 and is controlling for other predictors. Our null for beta 2 is beta 2 equals 0, where current poverty rate has no linear effect on crime, versus our alternative, where beta 2 does not equal 0 and is controlling for other predictors. Our null hypothesis for beta 3 is beta 3 equals 0, and police patrol percentage has no linear effect on crime, versus our alternative, where beta 3 does not equal 0 and is controlling for other predictors. Our null hypothesis for beta 4 is beta 4 equals 0, and there is no significant difference in crime between low and high poverty tier states, versus our alternative, where beta 4 does not equal 0 and there is a significant difference. Our null for beta 5 is beta 5 equals 0, and there is no significant difference in crime between mid and high poverty tier states, versus our alternative, where beta 5 does not equal 0 and there is a significant difference. Our hypotheses for the overall model using the F-test is where our null hypothesis is beta 1, beta 2, beta 3, beta 4, and beta 5 all equal 0, and none of the predictors explain variation in crime, versus our alternative, where at least one of the betas does not equal 0 and can explain the variation in crime.
My name is Brodie Hansen, and I'm going to be going through the first part of our assumption checking for this data. To verify that our model meets the assumptions of multiple linear regression, we ran a full set of residual diagnostics using R and generated the associated plots and test outputs for them. The first assumption we checked was linearity, which is that the relationship between our predictors and crime rates is in fact linear. To assess this, we plotted the residuals against the fitted values, as you can see in this plot right here. And what we're looking for is no kind of distinct pattern in the residual spread over this range. And that's exactly what we see. All the residuals seem to be pretty evenly spread around the 0 line and across the data. So that would suggest that we are, in fact, looking at a linear relationship. So we can assume that the linear assumption is satisfied. The next thing we checked was independence, which just means that each observation is unrelated to the others. This can't be directly confirmed from a plot alone, so we reason about it using the study design and how they collected the data. The data collected by Bothos and Thermopulos comes from 302 communities across 49 states, not including Hawaii. While the communities within the same state may share some common characteristics, like, for example, state-level policing policies or economic conditions, the data on different communities themselves were collected separately and represent different, distinct geographic areas, even within their own states. And while this clustering is a limitation that's worth acknowledging, as it may have some impact on relation between data points, we can assume, just based on the methods, as I said, of collecting data, that any impact there is very, very not significant. So therefore, we can assume that the independence assumption holds for this data.
The third assumption I'll be addressing is normality, specifically that the residuals are approximately normally distributed. To check this, we use two tools, a QQ plot and the Shapiro-Wilk test. Starting with the QQ plot, what we're looking for is whether the sample quantities of our residuals line up with the theoretical quantities of a normal distribution. In other words, do the points fall along the dashed diagonal line? In our plot, the middle portion of the distribution tracks the line very closely, which is encouraging. There is some deviation at both tails. The lower tail dips slightly below the line and the upper tail curves above it, but this departure is relatively minor and not dramatic enough to be alarming. The Shapiro-Wilk test gives us a formal statistical check. Our test produced a W statistic of 0.9795 and a p-value of 0.0003, which technically rejects normality. However, the W statistic being so close to 1 tells us the actual departure from normality is very small. The test is simply sensitive because our sample size is 302. And that brings us to an important point. With n equals 302, the central limit theorem assures us that even if the residuals aren't perfectly normal, our regression estimates and inference will still be approximately valid. So we conclude that the normality is reasonably satisfied. The fourth and final assumption is constant variance, also called homoscedasticity, meaning the spread of residuals should be roughly the same across all fitted values. Looking back at the residuals versus fitted value plot, we can see a slight fanning out of the residuals as fitted value increase, meaning the residuals become more spread out at a higher predicted crime rates. This is a visual hint of heteroscedasticity. The Broish-Pagan test confirms this statistically. We got a test statistic of 31.51 with a p-value well below 0.0001, which is a clear rejection of constant variance. This means heteroscedasticity is a real violation in our model. We are not applying a fix yet at this checkpoint, but going forward, the appropriate remedy would be to use robust standard errors, which account for this unequal variance without requiring us to respecify the entire model.
So, for our conclusion, today we introduced a 302 observation dataset on U.S. community crime rates across 39 states. We have identified total crimes per population as our dependent variable and defined all relevant variables. We have stated our research questions and formal hypotheses in beta notation and performed a full residual diagnostic checks on our baseline model. For our assumption check summary, our linearity was satisfied and independence was assumed, clustering by state flagged as a limitation. Our normality had minor violation in tails, and the CLT provided robustness at n equals 302. For constant variance, heteroscedasticity was confirmed via the Bruch and Pagan test.